The human body is an integrated biological network, operating on strict energetic and temporal budgets to maintain homeostasis. During Ramadan intermittent fasting, or RIF, this budget undergoes a shock. For 29 to 30 days, food and fluid intake are restricted from dawn until sunset. Pituitary gonadal axis, the complex feedback loop connecting the brain and ovaries that regulates female reproduction. This reconfiguration reveals a clinical paradox. In healthy women, the sudden energy restriction can trigger reproductive irregularities. Yet in states of metabolic dysfunction, this exact same disruption acts as a stabilizing force. We will deconstruct the underlying mechanisms to map exactly how fasting mechanically alters reproductive endocrinology. We will track three intersecting pathways: metabolic signaling, the neuroendocrine stress response, and circadian recalibration. By isolating these pathways, we can observe the multi-vector reprogramming of the body's reproductive operating system. This diagram shows the baseline architecture of the HPG axis in a normal caloric or normal feeding state. Signals cascade downward from the brain to maintain continuous hormone production. Clinical data from Vafai Nishad and colleagues reveals the first major systemic outcome when this baseline is subjected to Ramadan fasting. This chart illustrates their findings. Premenopausal women experience a systemic decline in circulating estrogen levels. This drop is selective. While estrogen falls, the trend line for progesterone remains flat during the same fasting window. A secondary clinical data set from Luigi Vato tracks a separate biomarker that responds to the fasting window. That variable is sex hormone-binding globulin, or SHBG. This protein binds to sex hormones in the blood, controlling how much of them are actively available to the body's tissues. As this chart shows, intermittent fasting triggers an upward surge in SHBG synthesis. Because SHBG binds to androgens, this increased synthesis reduces the amount of bioavailable testosterone circulating in the bloodstream. What physiological mechanisms translate the absence of food into these specific hormonal downregulations? The answer begins with the biological sensors designed to monitor energy sufficiency. The observed drops in estrogen and bioavailable androgens are measurable outputs of the HPG axis reacting to environmental deprivation. We start at the highest level of the architecture, the hypothalamus. This region acts as a master switch, using metabolic hormones to gauge if the body has enough energy to afford reproductive functions. The two primary energy signaling molecules the hypothalamus tracks are insulin and leptin. Leptin is secreted in proportion to adipose tissue mass and immediate nutritional intake. These molecules regulate a process called GnRH pulsatility. GnRH, or gonadotropin-releasing hormone, is released in rhythmic pulses to stimulate the pituitary gland. In a fed state, high leptin levels maintain a rapid, rhythmic pulsing of this hormone. During the caloric restriction of Ramadan fasting, circulating insulin and leptin levels plunge. This loss of leptin stimulation physically slows the GnRH pulsatility. These weakened pulses hit the pituitary gland and dampen its release of downstream gonadotropins, specifically luteinizing hormone and follicle-stimulating hormone. Without sufficient LH and FSH, ovarian steroidogenesis is suppressed, explaining the initial clinical observation of dropped estrogen. The reproductive system is wired to shut down energy-expensive processes like ovulation at the molecular sign of metabolic scarcity. Biological deprivation functions as a state of environmental stress. The body interprets the absence of energy as a systemic threat. This activates a new element in our endocrine map, the adrenal pathway. Shifting sleep patterns and energy restriction trigger an elevation of cortisol. Cortisol functions as a systemic override switch, prioritizing immediate survival over reproduction. Elevated cortisol inhibits both the hypothalamic neurons producing GnRH and the receptor sites on the pituitary gland. This mechanism leads to a condition known as hypoestrogenism, a state of abnormally low estrogen levels in the bloodstream. In healthy women, this cortisol-induced blockade correlates with potential anovulation and cycle irregularity. While metabolic sensors throttle the system down, the neuroendocrine stress response uses cortisol to blockade reproductive function. We must also account for the timing of consumption. Ramadan restricts meals exclusively to the night. The HPG axis operates on a 24-hour circadian rhythm, synchronized by daylight and digestion. This synchronization relies on circadian entrainment, the process by which internal biological clocks align with external environmental cues. Shifting food intake away from daylight hours forces a recalibration of this metabolic circadian entrainment. An emerging piece of this temporal puzzle is the gut microbiome, as tracked by researchers like Lin and colleagues. Fasting alters gut microbial compositions, which secrete metabolites that interfere with hormonal signaling. These metabolites interact with thyroid hormones, further altering the secretory patterns of reproductive hormones. Ramadan fasting decouples the reproductive system from its biological clock, proving that the timing of energy intake is as critical as the volume. We have built a complete view of the architecture: metabolic downregulation, cortisol blockades, and circadian decoupling. This returns us to the paradox. If this architecture suppresses the system, why do clinical outcomes vary among different populations? The impact of fasting is dependent on the starting baseline. On the left is a healthy normocaloric model. On the right is a dysregulated model. When we apply the fasting framework to the healthy baseline, the suppression drives hypoestrogenism and cycle irregularity. The dysregulated model often suffers from a hyperandrogenic state, characterized by excessive levels of male sex hormones like testosterone. In this baseline, obesity alters normal profiles of LH, FSH, and testosterone, creating erratic feedback loops. When the fasting suppression algorithm runs on this hyperandrogenic system, a spike in SHBG binds the excess testosterone. Dampening these signals stabilizes the androgen profile. As the month of Ramadan concludes, the body transitions out of this period of strict energy restriction and returns to a normal normocaloric routine. Intermittent fasting acts as an endocrine tool that suppresses physiological pathways, a mechanism that can disrupt a healthy system or recalibrate a dysregulated one.